right, so thanks everybody for attending, and thanks for the introduction. So today I'll be talking about local MCMC, sequential MCMC for data assimilation. This is something that I think unusual for most of you. Usually people use the ensemble Kalman filter methods or particle filter. So this is based on some work with collaborators from Imperial College London and UCL, and as well as Omar Knio from KAUST. In particular, the localization is only with Omar. Okay, so as a motivation, if we look at these two pictures here, on the top we have some observations in the yellow circles coming from Argo floaters in a window of 5 days. And if you look down, we have these lines coming from the so-called surface water and ocean topography satellite by NASA. And if you look at the data, they are very localized compared to the region of interest. And this suggests that one can apply some kind of localization to reduce the cost of the algorithm. And the algorithm I'm interested in is the so-called sequential MCMC, which we introduced in a previous paper. So it will be very similar to what Ilyana did. So we will cut our domain into subregions and then do some local updates in these regions. So let me start with the regular state space model. I have a hidden continuous time stochastic process ZT in RD, but we are interested in the values of these hidden states only at the time of assimilation, so T1, T2, up to some known time. So the dynamics looks like this. Z at time Tk is some physics of the previous state plus some noise, WTK. And WTK here is a noise with a zero mean and covariance matrix Q, but doesn't have to be Gaussian. And this equation actually induces the so-called transition density, which gives me the probability from going from ZTK minus 1 to ZTK. The second component of a state space model is the data model. So a sequence of real observations, YTK, coming from some observers, and at time T1, T2, etc. YTK belongs to RDYK, and here K indicates that at some time, like at times, the size of Y could be different from previous times. So this allows for kind of time-dependent algorithm. And also we have a model for the data. So YTK is some operator of the applies on the state ZTK plus noise of zero mean and covariance matrix RK that not necessarily Gaussian, and this will introduce a likelihood density that measures how close is the state to the data. The goal is to estimate the filter distribution, which is a conditional distribution, the probability of the state at time Tk given all the data up to the current time at the assimilation times. So if we take WTK to be just Gaussian, then our transition density is going to be Gaussian with mean phi ZTK minus 1 and a covariance matrix QK. Similar to the data model, if the noise is Gaussian, then the likelihood density is going to be Gaussian, and this is the mean, and RK is the covariance matrix. So we assume that we know F and J, F and G. So this is something needed up to a normalizing constant, of course. So the goal is to approximate this conditional distribution. So in this method, we try to avoid using the particle filter or other methods where we have to use to do importance sampling and resampling, and this will generate weights. However, in this method, there is no weights, so we avoid the weight degeneracy issue, especially in high dimensions. So the filter at time one, filter distribution at time one, and I got rid of the dependence on y here to make the notation short. So at time one is just the transition density going from Z0 to Z1 times the likelihood density Z1 and Y1. But when K is greater than or equal to, then it's given in this recursive formula. So we see here an integral of RD transition density times the previous filter at previous states. So what we're going to do is we're going to approximate this integrals or this filters. What happened to the screen? Using Markov Chain Monte Carlo. So Markov Chain Monte Carlo, it's a powerful sampling method that's used to sample from complex distributions, especially in high dimensions. And by designing a chain initialized at some random value, and eventually this chain will generate samples from your distribution. So the sequential MCMC algorithm in this paper starts like this. So at time one, you run an MCMC algorithm for n plus n burn steps to sample n samples from the filter distribution at time one. And this is done exactly. There is no approximation for the filter distribution. However, when k is greater than or equal to 2, we're going to replace this by using the samples from the previous step. So we're going to put an empirical measure here that's centered at the previous samples from the previous time step. And this will kill the integral and result in this simple formula with this summation. However, now remember I need to sample n samples from this distribution. So for each sample, I need to compute this n summation, which means I need to evaluate f n times plus the evaluation of g, of course. And this will result in a cost depends on n squared. A way to get rid of the square is to notice that this approximation is actually a marginal of the joint distribution over RD and the integers from 1 to n given in this red equation. So if you take the summation here over I from or over j from 1 to n, you go back to the top approximation. Now this in this one, what we need to do is we're going to sample j and ztk simultaneously. So we first sample j, and then once we do that, we pick only the sample from previous time of index j inside f, and then sample ztk in an MCMC fashion. So that's what I said. Now, one issue in MCMC is that in order for this method to converge, you need to set n to be very large, in thousands, even when the model is small. A dimension of the model is small. However, there is a nice thing that you can actually create m parallel chains and divide this n by m, where m is the number of cores available in your machine, and then get the samples from these m chains and stack them together, and you get the samples from this joint distribution. And the cost of the algorithms, the algorithm will range from n over md to n over md squared, depending on the structure of the state noise covariance matrix. This d comes from, or d squared comes from the cost of computing the transition density f. So which actually involves a matrix times a vector. So if a QK is nice, then it becomes a vector kind of times a vector. But if QK inverse is dense, then the cost is of D square. But in real life applications, usually this covariance matrix is very simple, and we are in this region. So linear in N and linear in D. So the algorithm is like this. So from time 0 up to time t1 minus delta t, where these are the time steps between the time 0 and the first time assimilation, you just forward the model by forwarding the dynamics up to time t1 minus delta t. And then at time t, you generate M chains of MCMC by going serially for each chain, start from some initial point and until you get to ZT1, for example, N11. This is, so you got here N1 samples from the first chain, and you do the same for the rest of the chains. And here you get NM samples, and stack all of them together, you get N samples from the first distribution, then evaluate the mean. I should put a bar here to indicate that we are interested in the mean of this filter. So the mean will be just the average of these samples. Now for next time steps, it's more complicated. So now you have N samples stacked in one vector. You're gonna run all of them, you forward them in time in parallel. But however, we can do, as I said, in parallel, if you have N cores, then this going to be cheap until you reach T2 minus delta T. And at time T2, I'm going to do the same. I'm going to run M chains of MCMC and finally stack all of them together in one vector and then get the mean of the filter to be the mean of these samples. So let me show you how we construct one of these chains. So we're going to sample J and ZT2 from this distribution using MCMC. So we first sample G, and we sample J. For example, in this case, it's 2. So we pick the sample from a time T2 minus delta T of index 2. And this will be here. Then we sample ZT2, and then we move. Now we sample J2, which is 4. So I pick the fourth sample from the previous time step, and then I generate ZT2, 1, and so on and so. So now this is gonna quickly talk about this, the convergence of SMCMC. So if we denote the mean of some function phi with respect to pi by this, then we have this proposition about the convergence of this method as n goes to infinity. And yeah, so as n goes to infinity, we have almost sure convergence. Now, let me quickly go to the localization of this. So as I mentioned before, when the data is localized or sparse, we propose a localized SMCMC method. And this will result in a reduction in the effective states dimension from D to D prime. And so the cost will be n over m d prime now. And if the covariance matrix is dense, then n over m d prime square. So let's look at this example on the right-hand side. So I have two arrays of observations. So this is like mimicking the SWOT mission by NASA. So the data here are the black dots. So you divide the whole domain to gamma subdomains, And then you're going to pick the domains that contain observations. So my domains of interest will be the blue, the green, and this light gray. Now, we let xtk bar denote the collection of grid points inside the choosing subdomain. So, for example, I will choose all these points here from x0, x1, x2, up to x22, and the points in the green, and the same thing here. So all of them, denote them by xtk bar. Then I'm interested in the state variable at these locations. And inside now by kn, I'm only gonna update these variables at these locations. And so we are kind of reducing the dimension to d prime here. And same thing gonna be done for G, the likelihood density. And the way to do that is actually by cutting the rows and columns in the QK inverse matrix and keeping only the ones that correspond to these locations. Okay, now I will show some numerical examples. I think I have a minute or two. So first I start with a linear example because the Kalman filter is exact there. So the dimension here is 10,000 and it's a very simple model. A here is just a constant and sigma is a constant. The observational model also looks like this. C is a matrix of ones and zeros, and sigma y is the standard deviation in the noise of the data. I'm going to consider swaths of data moving periodically from left to right. So at time 6, I have this blue. These are from previous time steps, just to show you how it looks like. So at time 11, it looks like this, and at time 14. And I compare between the methods, the SMCMC, the regular eNKF, and a local eNKF version, which I got from this paper, which is an R localization scheme. So here I wanted to make all of them give me an error that's bigger than 70%. So what's the percentage, or what's this? Sorry, so what's this? This is 70%. I want 70% of the errors to be less than sigma y over 2. And when I say the errors, that means at all state variables and all times. So I make a histogram, then I measure the percentage of these errors. So I wanted them to be, the errors to be that are less than sigma y over 2 to be bigger than 70%. And that was the time needed for the method. So for this one, for eNKF, it's 145 all of them 145 seconds. However, I got for the LSMCMC with setting gamma to be 1,156. I got 99.79% of the errors less than sigma y over 2, while it's 70% for eNKF, and local eNKF is 73%. Now, I want to set the number of samples to be the same. So I set n to be 5,000, and so for the eNKF and the local eNKF, it's called in simple size. And I got these times and these percentage of errors. So for the LSMCMC, it's only 145 seconds to get 99.79% of the errors less than sigma y over 2, while for the eNKF, it's about 485 seconds to get 93% of the errors less than sigma y over 2. And the local eNKF with different number of subdomains, I get these times and these percentages as well. So we see a big advantage for using LSMCMC, even though this model is actually linear, but very challenging because of the structure of the data that moves with time, and it's very localized. And here's a picture of the So on the left, I have the Kalman filter, the true, and here I have LCMCMC, and here SMCMC, and the ANCAF and the local ANCAF, and here's the difference between these two. Finally, let me show you a nonlinear model, so the rotating shallow water equations, and this is going to be in high dimension. Also,
sorry, Hamza, probably best to conclude because we're all pretty much out of time, if that's okay.
Okay. So this is for the shallow water model with synthetic data also periodically move from left to right. We see a big advantage compared to SMCMC. Also, when we have drifters, this is real data in the Atlantic Ocean, some region Atlantic Ocean. Also, we see a big difference in the time between LCMC and SMCMC to get the same results. So finally, let me conclude. So in SMCMC, the cost is of order N over MD, where M is the number of cores available, and N is the number of samples, D is the dimension of the state. When you do localization, then this is going to be reduced to N over M D prime, and D prime is supposed to be much less than D. So I finish here. Thank you for listening.
Okay, thanks very much, Hamza, for the very interesting talk. I think in the light of time, maybe we can do the questions offline for this talk, and perhaps we move on to our next speaker.